I am the only person standing between you and lunch right now. I am going to take that responsibility seriously. Additionally, my body thinks it's 3 a.m. right now. So if I'm being a little weird, that's where that comes from. My name's Tanner Lund. I work for Indeed. More of my bio won't matter to you until you know whether or not what I have to say is interesting or not. But we're going to talk about functional resonance analysis in sociotechnical systems. Big, fancy words that will make more sense in a minute. I will be inviting a little bit of group participation, but it will be simple. It will be of the kind where you just shout out something short and appropriate, please. And I will repeat it so that it gets caught on camera and microphones and everything. So what is a sociotechnical system? Right? Sociotechnical system, there's fancy definitions. I was going to put in one from Wikipedia, but I felt like it made things more confusing rather than helpful. Our shorthand is basically, a sociotechnical system is a system where you understand that there's things, but also that there's people, and that they're part of the system as well, that you need both pieces of it. Right? We're not talking about just the people as a system. We're not talking about just the technology as a system. We're talking about it all together because it's interconnected and interdependent. This is an example of one. My objective for today, for the next 23 minutes and 23 seconds, is to teach you to interpret what you're looking at right now. This is a functional resonance analysis method model. In 20 minutes, this will be discernible for you. I want you to be able to reason about it. I want you to be able to understand at some level the behavior and dynamics of the system it represents, even as an outsider, to that system, to apply the method that created this to your own systems, and to evaluate, most importantly, whether or not that's worth doing. Right? I'm going to teach you a skill today, but I also want you to be able to reason about whether or not it's appropriate or useful. So, this method comes from Dr. Eric Hollnagel. The short name for it is Fram. So when you hear Fram, it's this method. That's the cover of the book. Highly recommend it. Also, this QR code thing. That is a handout, a digital handout, just a Google Doc, with a bunch of links that are relevant and references. There is certain software, free software you can download and use to help build these kind of models, all that kind of stuff. It will be on some of the slides, but not all of them, so good luck getting your picture. So why Fram? Right? Why would you do Fram? Right? We need a little bit of context. You're not even going to care to learn how it works. Right? And fundamentally, it's the question you should be asking is it good to think with? Does it help you understand your system better? Right? We want to learn from incidents, but we also want to learn from normal work. Incidents are a very good opportunity and excuse to dig into our system more on company time. It's great. But you don't have to do it in the context of an incident. You can do it at any time. One of the reasons why Fram exists is to acknowledge that these socio-technical systems are complex, they're interrelated, they're nonlinear, a bunch of things we heard about in the keynotes earlier today. And we have relative ignorance about our systems as a whole. We understand certain pockets of them where we have expertise, but not the whole. I'm not promising that you'll understand the whole afterwards, only that you'll be able to broaden your understanding a little bit and know who else might know some more to help you. And intractability as well, right? So here are these principles. And Dr. Hollnagel always emphasizes that this is a method sine model, not a model cum method. And I'm not the Latin speaker here, so Google it. But first principle, we want to look at functions, not components. This is something that is somewhat reductionist in that it breaks things down into pieces so that we can analyze them. Is that fully representative of the real system? No. Is it helpful anyway? Maybe. We're going to try. I've found it to be helpful in certain circumstances. But what this does is if you're thinking of like nodes and lines, the nodes in this are functions, not components. You're not going to draw your database. You're going to draw a transaction. So next principle is that failure is equivalent with success. Fram doesn't care about whether or not an operation succeeded or not. It doesn't even think about things in those terms. What it has is output from functions and the variability in that output. right? The output from waking up can be that you woke up on time, woke up a little bit late, or woke up infinitely late, as in not at all, right? And it has no value judgment as to whether or not one of those was good and the other was not. It simply has output and how it varies. And that output gets plugged into another function and therefore affects it. You see how we can get to some weird chaining and looping dynamics here? So another principle is emergence, which has been mentioned several times. I'm just going to give my little version of the spiel here. Right? Emergence is properties that arise from the interactions, not from the individual pieces. So if our individual pieces, in this case, are functions, we see emergence from the interactions between the functions. Example here, there's cellular automata. Is anyone familiar with cellular automata? I don't know why I asked you to raise your hands. I'm going to tell people what it is anyway. But there's these have been around for a long time. If you look at the one on the left, it's kind of a grid, and there are rules about certain squares that get evaluated for every tick of the clock based on its neighbors. It says, are my neighbors, do I have 3 black neighbors and 1 white one? Or they could be ones and zeros, or however you want to represent it. And then according to some logic rule that you've built in, it itself will change to white or black, or 1 or 0. The most famous version of it is called Conway's Game of Life. It's a very nice set of rules that creates all sorts of interesting nonlinear behavior, things that are called shooters and flyers, and fly around the screen. And you can have chain reactions that go on for basically forever just from these very simple rules. Emergence from the very simple rules. The one on the right is just, I just think more people should know about it. It's an enhanced version of cellular automata. It's called Linear. And yeah, that's cellular automata right there, with the grid system and everything, but new and improved. So you can go really far with these kinds of things. Next principle, resonance. Throwback to Physics 101. When you've got functions, you've got these waves, you can have 2 waves that hit each other, and they can have constructive interference, where the 2 waves kind of combine together to be big waves, or you can have perfect inverse of that, where they cancel each other out. And so you've got something flat, and you have everything in between. And we're thinking about the variability of outputs from a function. You can have a variable function that combines with another variable function to be real crazy. Or you can have a variable function that dampens the variability of a different function. So this is all very abstract, right? Let's get into the meat and potatoes here. Fram models themselves. This, right? We got to learn how this works. I've got 17 minutes left. We got to go. Hexagons, right? Let me go back, right? That's full of hexagons. Hexagons. This is the core representation here. Each hexagon is a function. Each corner represents something that has to do with that function. We're going to go through them one by one here. First is input. Input is not just something that goes into the function, but is also, roughly speaking, the thing that kicks off the function. So if you want to open a door, what might an input to that be? Just shout out any random thing. Pushing it. Right. So, and then the output then would be, in that case, would be that the door is open, right? In the case of lock the door, the output is the door is locked. You can have multiple outputs. You're not supposed to have multiple inputs, but you can always fudge these things, because the point is it helping you to learn about your systems. So, next one is resource. Resources are things that you need in order to do the function that are consumable. If your function is drive to the job site, you have to have gas in your car. And you see where some of the variability in this might be. Maybe you have a lot of gas, maybe you have a little, and you're going to need to stop for more along the way, so on and so forth. If you're saving a file, you need storage capacity that eventually is consumed. I know it seems like storage is infinite sometimes, but it's not, I promise. So resources, consumable things that are necessary for the function to do its thing. Preconditions, non-consumable things that the function needs to do its thing. Sometimes these get confused a little bit with inputs. An input is basically a precondition that feels like it's starting the function. Everything else is a precondition. In an example, and this comes from the book, actually, right? There was an example of like a surgical system that's happening, like a process for surgery. And the input for close up the wound is tissue extraction was completed. But as a precondition, you're supposed to check for all surgical tools so you didn't make sure you didn't leave one inside and apply the analgesic. Is that starting to make sense? A little bit, maybe, right? I want you to be thinking about analogies to software systems and sociotechnical systems. I'm using these simpler examples. We're going to get more software as we go. And then time. And an example of a system of a ship that goes places, time is the ship sailing schedule. It's like, well, we're supposed to leave now, right? It's not really an input into the function. It's just, well, this is when this is supposed to be happening. Why hasn't it happened yet? So on and so forth. Final one is control, right? It's your run book. It's the ship's standing orders. It's the code deployment configuration. Control is how do you do the thing? And according to what rules you can do the thing. So you start connecting these. You've got verify system health as a function whose outputs, here's some faults that need addressing as an input to create initial mitigation plan. When you want to study your system, it's iterative. You start somewhere like that. You can, if you want to start from an incident because it's more tractable for you that way, you can start with an alert fired. And then just kind of work your way through adding functions as you go, even if it's mostly input to output to start. And then you can go and you can do a back pass or you can do a second pass. And you can kind of just flip through it until it starts to feel like it's meaningful. What granularity you should use is kind of up to you. Because these can be broken down into smaller substeps, right? And it's up to you to determine what is the distinction between a function and a subtask. And it has to do with all of the other lines that are going to come out of it, right? Is the time different? Is the control different? Are the resources or preconditions different? If so, maybe it deserves its own hexagon. If not, maybe not. So you can start growing this bigger. This is an example of another system. And by the way, all of these that I'm showing are not indeed systems. So please don't assume or read into anything too much. But this is an example of a system from somewhere else that takes data from certain storage clusters and backs it up to Azure. And this is only like the top corner of one of these systems. But just look at that for a second, and you can kind of see outputs going into inputs. You can, one thing that I noticed when I started building things like that is like off is an input all over, like it goes in as a precondition to so many functions, right? So part of this is it's exposing dependencies a little bit. And then when you look at this, you can start thinking about what are some chain reactions that could happen if something's output was unusual, right? If we go back to this one, this big one that I keep showing, this one is an incident response process. Right? This one is more people than software, but again, I'm not specifying either. I'm not saying who's doing this or what tools they're using, merely that the functions are happening. And this is, again, a simplified version. This is the point we're at. So when you start to get something that gets to this side, where you feel like you've got what you need, let me hit one final detail here. As I'd mentioned, each hexagon, in theory, each function is supposed to have an input and an output. But eventually, you have boundaries of your system, right? Everything is connected infinitely, but you're not going to map the whole universe, right? So you have boundary functions who are the terminus or the beginning of your system. They're special in that way. But everything else, you should try and make sure has inputs and outputs. Otherwise, it's explicitly saying, this connects to some other system. But once you get to that point, you can peer review the model with someone else. Like I said, this is not meant to be canonical. This is what your understanding or your team that's building this together's understanding is of how the system looks. If someone else with different expertise builds it, I would expect it to look different. That's a good thing. And when you look at the two, you should be able to infer something from the differences. Does that mean you should meld them together into one master one? Probably not. I think the diversity of them is useful. It's the exercise, it's the method of doing this analysis and building these models that's valuable, not the artifact itself. So, how do you do an actual analysis? Like you're trying to build this thing. Well, step one is, as I'd mentioned, you identify and describe the functions, right? You draw a circle, that's a function, and then some other function, I'm not quite sure what it is, and then draw the rest of the smiley face, right? You can fudge things, and then in a later pass, go in and fill them in as you understand what you're dealing with a little bit more. You need to be willing to iterate, to do a pass, look at it, say what's missing, and also to define the boundaries. Where are we explicitly not going to go? What are we explicitly not going to map because it's not relevant to the questions we're asking about how our system works? And then identify variability. So thinking about, and you don't have to derive it from this one, but thinking about an incident response system, what's something that could be highly variable? Just shout it out if you think of something. How quickly you can get an expert on the call. Right? Let me see if I could, is that there? Do I have that one? Let me see. Yeah, escalation to a partner team, you could squint at and say maybe that. So if there's variability into that, what does that affect afterwards? Right? Well, the partner team investigation, right? And so if that's delayed as well, what does that affect? It affects the partner mitigation steps, but it can also affect system state changes in other ways, so on and so forth. And you can kind of see how the rest of the incident process is affected by that. Even if it was an event that took 12 hours, you can still be feeling the effects of this much further down the line. Or conversely, depending on how your system's set up, that might have been dampened. Like maybe it took a while to get them on the call, but you're able to get them up to speed relatively quickly, and so it's kind of a wash. This is a big piece of it, and this is a lot of what's in the book, and this is part of what's maybe not as fun to talk about in a talk, but it's worth sitting and thinking about, is then you think about the different types of input and output variability for those functions. So in theory, and please don't overthink the categories, this is an opportunity to look at things from different angles. The buckets don't really matter. It's just look at it from this point of view, look at it from that point of view, so on and so forth. So internal variability, this function in and of itself, how much does it vary, right? In that case of how long it takes to get an expert on the phone, the internal variability of that, what drives it? Conversely, what is the external variability of that? What other functions affect that? Is your phone system down? Is this expert not on call but happens to be the only one who knows how to deal with this, and so they're asleep, so on and so forth. And then it gets really fun when you look at upstream, downstream variability. The stuff that's within your system is like, this is variable a lot, probably because of this thing 2 functions back. Or if this is weird in this one way, it will affect the rest of the process. Again, this is an approximation. This is can we learn some things about some properties of our system, not a canonical, this is how it works every time, and I know my system perfectly. Right, it's a model. Some examples are with the timing. I kind of mentioned this earlier. You can wake up too early, you can wake up too late, you can not wake up at all, which is just a special case of too late. Things can be in a different force, distance, or direction, right? Something could be too weak or too strong. Was it earlier today? There was the mention of a recovery, like recovering too well, and bouncing back too much, and that causing other problems. Something your output could be in the wrong direction, or be of the wrong type. It could be the wrong object, right? If you're outputting a credential, it's outputting the wrong credential into the next function, for example. Sequence matters, right? This is where a lot of the lines matter. Omission. Skipping is not quite the same as omission. It's skipping a piece. Omission is skipping the whole thing that it's expecting. There's repetition, there's reversals and swap. Like, I'm starting to think like network packets and stuff here, right? You can have an additional wrong object. How do these different things affect it, right? Pages, for example. If you don't get a page, or you get a page but you're missing like any of the content in the body of that page, or it's pointing to the wrong conference call to join, or you get a storm of pages, so on and so forth. And then you ask, how does the variability of the output affect the downstream functions? Does it make everything else more variable? Does it have a dampening effect on it? So there's a handout for this. As I mentioned, the QR code that's everywhere. I promise there's no actual self-promotion on it. It's just a list of resources that are pretty helpful. The software that I use to build the examples is there. It's free. It's a little bit older. I kind of want to build a new one, but I didn't build that one. But there's a suite of things. There's also something called Fram, because you can walk through different instantiations of your model. You can say, OK, here's an actual incident. I already have a diagram of the system I did previously. Let's walk through with this incident and see this output varied in this way. It connected to this. It turns out that we needed this resource, and I'd completely forgotten about it. So let's add that in. And then let your incident teach you about the system that way as well. So when should you use Fram? When you find it helpful. Right now, we're open for questions. The questions primarily, I would like them to be ones about how to do it, but if you have criticisms or general philosophical things, please do as well. But you're going to shout them and I'm going to repeat them into the microphone, so we'll need to keep them succinct. We've got 3 minutes, and I'm not going to sing karaoke to fill up the 3 minutes if you've got no questions. If there's any slide you'd like to see again also. Yeah?
This looks great. Thanks for the talk. It looks also like a lot of effort.
Yeah?
To do something like that. I wonder if you have any sense of under what circumstances you would recommend doing it. When would it be worthwhile?
Right. So the question is, because it looks like something that takes a lot of cognitive work, when is it appropriate to do this? The short answer is when the team feels like it would be sufficiently helpful. But when you have a lot of questions about how things connect to each other, when you have folks that are newer to a team and are trying to build their mental models, when you can repeatedly find through your incidents that things don't work the way you think you do, that's an invitation and an opportunity to sit down and map that out a little bit. Now, that doesn't make it a replacement for the existing incident response processes, and you can do a lot of that without having to use Fram. But that's one of the places where Fram can fit in. It's saying, you know, I really need to sit down and think deeply about this. I can use this framework to do so, and I'll have an artifact at the end of it that can remind me, that I can teach other people with, and that is a demonstration to management that we've done this cognitive work. Right? That's the little side benefit, is that you now have an artifact that shows the time and effort you spent trying to understand your system a little bit. Whether or not they can read it, they can at least see that it's there. Is that helpful? OK. Minute and a half left. Lauren, go ahead. A specific insight that I've gotten from these models. Yeah, a specific insight I got when building this one about incident response is that there were a lot of interdependencies that I didn't actually notice were there. Even though I had done a lot of incident response and I was an incident commander at Azure for a long time, and that was not an on-call, that was an on-shift, even though they called it on-call. There was a lot to do. I kind of touched on this a little bit before, but realizing how much auth touches, like it should be obvious, but seeing it drawn out, it was like, oh, if auth is down, everything's down. Similarly, the one about the data backup system, the network. If you've got network problems, even if they're just network problems at the home of the engineer who's working remotely because of the backhoe, it's going to affect everything else. That sort of thing. Again, maybe that doesn't feel that insightful to someone who already understands it, but for me, it was a little bit of an eye-opener. 30 seconds. Alex. Is it best done solo or collaboratively? I think most cognitive work is helpful to do collaboratively. It depends on how you want to do it. You can do it solo and compare notes, or you can sit together in a room and do it. There's probably limits to the number of collaborators, though, but both are valid. But remember, the contrasting perspectives is valuable. And that's all the time we have. Thank you. Did you learn? Do you think you could do one of these? Do you think you could draw one? Good. You should try. There's homework in the handout. Now go eat lunch.